Hello, ladies and gentlemen. Welcome on my second part of Atomic Matter's computation system tutorial. And today I'm gonna to tell you about calculations and calculation parameters. First of all, we have to choose object of calculations. We can freely choose anyone from periodic table of elements. For example, here is cobalt. If we push one of button here, we establish cobalt 3 plus ion as a object of our calculations. Now we have to decide which calculation base we decide to use for further calculations. Base JJZ is the base for splitting of the lowest multiplet, but calculation in whole LS, LZ, SZ base is calculation of lowest term with whole multiplet structure. Of course, in the general case, using LS base is better than JJZ, but for the historical reason, there is a very big data of results of calculations for ions in JJZ base. Of course, the most important thing is physical adequacy of such calculations. In case of cobalt, it's very bad example of JZZ calculations, because for 3D ions here, J is it not good quantum number, so for calculations the group ions in solid matrix we can be very careful and don't use this base. The opposite situation is in the 4F and 5F ions from lanthanide and actinide groups, where JZ calculation is a standard now, but of course using LS base is of course better. Next important field is the selection real or complex field of matrix elements. When Hamiltonian matrix of crystal electric field and spin orbit calculations will be created, the field of elements will be established on real or complex. Those situations differs because calculation in real field of matrix elements provides information about magnetic properties of materials in two perpendicular directions, but calculation in complex field for matrix elements provides full 3D information about magnetic and other direction properties of calculated material. Next selection is the method of inputting of crystal field parameters. There is a free base way to establish crystal field parameters. In the atomic matrix computation system, we are using Stevens convention for crystal electric field parameters. So the simplest way is the filling values of parameters in the fields. Of course, the unit used for calculation can be chosen from between Kelvin, millikelvin, and millielectronvolts. The very important thing is choosing the symmetry of local surrounding of ion. So when we choose tetragonal symmetry of surroundings, we can see 1, 2, 3, 4, 5 parameters describing such symmetry. In cubic field we have only 2 parameters, depends on direction of z-axis. We obtain different set of parameters. For example, if we put here reasonable value of parameters along direction 011 in crystal, we obtain such set of parameters. When we change directions, numbers of parameters will increase. Those sets of parameters describes the same crystal field and gives the same energy level scheme. Those sets of parameters describes the same crystal field and gives the same energy level scheme in results. It's worth to know that external magnetic field coordination corresponds with x, y, and z axis along 1001, 010, and 100 axis directions in crystal. Let's perform calculations. It's really fast, and in a matter of seconds we can see the results. That was definite field. Here is energy level scheme, spectroscopy, magnetic susceptibility, inverse susceptibility, and so on. It's clearly visible that cubic crystal field doesn't give any changes in directional properties. But when we back to the parameters, the list of parameters will increase, and contains whole possible parameters for triclinic free symmetry. It's because it's easy to change values of crystal fields for experimenting with energy level scheme and other properties. Of course, that's not only one way to establish crystal field parameters by atomic matrix computation system. Second one is point charge model approximation. When we click this button, we can establish crystal field parameters by a completely different method. For example, if we use point charge model, we can slightly estimate value of crystal field parameters according to distances between coordinating charges with dedicated values of charge. For example, if we put here 1 angstrom for the distance between coordinating ion and point charges, we can obtain such set of parameters. Those parameters can we use for construct full surroundings contains, for example, cubic center and second second zone made by two charges by 2 angstrom, and sum of those parameters it's here, and those parameters we can send to calculation to the panel with Stevens parameters, or send to visualizer directly. When we do this, we can do many things with visual side of this calculation, and here we can change its values of parameters, of course. Now you can see how view of crystal field is changing when we changing parameters. Those parameters still can be sent to calculations, and now we can recalculate them as follows the equalization process. So when we put any value, for example 1.5, whole parameters will be recalculated according to this factor. And now we have set of parameters, and now we can start calculation. But when we put this button, we obtain another set of parameters, but this button override existing set of results. That was our crystal field splitting. Now we can observe some anisotropy in magnetic susceptibility curve. Inverse susceptibility allows us to observe values of two directional values of effective moment. It's very informative is effect of using changing of base of calculations. So when we use those parameters for current ion, and we change base for LS, automatically spin orbit coupling constant will field as a free ion value. Let's change base for complex for full calculations, and let's start again. Complex calculations in full base takes some time, much more than JZ real calculation, as you see. But after 23 seconds, we can see structure of levels in the same scale like before. Okay, at the end I would like to show you one more interesting feature about input parameters describing crystal electric field. In references in scientific papers, you can find many of conventions to describing crystal electric field. Factors for calculating conventions we have found and put into this calculator. So if you find, for example, such kind of operators of that one, you can put it here, and values and values in typical used atomic matrix convention can be exported to calculations. Of course, it's important field, complex and real, to establish during exporting, importing set of parameters in application. That was all for second part of our tutorial. Thank you for your attention. Bye bye.